In this lecture, I will prove that electric field is a conservative field. First of all, let me share what is the meaning of a conservative field. A conservative field is that in which work done in moving a body is independent of path along which the body moves. Such a field is called conservative field. We have to prove the electric field is also a conservative field. For this purpose, let me consider coordinate system x-axis, y-axis, z-axis. Suppose a positive charge plus q is placed at origin of the system. It has a field around it, that is electric field of this source charge. Suppose a test charge is moved along an arbitrary path from point A to point B. Let us suppose body is moving via any arbitrary path. On the path, let us consider any point P having distance r from the source charge, and the test charge is q naught, which is unit q naught positive charge. Test charge is always taken as positive. At this arbitrary position P, let me consider a small displacement, that is dx vector. So let me call this point P, and the end we have P dash. Now I will draw a perpendicular from P dash onto this line. Let me call this foot of perpendicular as M. So let us zoom out this diagram. It will become more clear. P is point here, P dash is here, and this is R, and this is perpendicular, and this is point is M. Let us suppose this angle inside this triangle is theta. If I produce it next, in which we have electric field. Electric field is in this way, because electric field from the source charge is a straight line in this direction. So this external angle will be 180 minus theta. Now let us calculate small amount of work done. Small amount of work done during displacement dx vector. We have to calculate how much work will be done when I move test charge plus q naught from point P to point P dash. This vector P to P dash is nothing but dx vector. By definition of work, I can write dw equal to f vector dot dx vector. Dot product of force and displacement is called work done. Now angle between force, this first of all let me put f vector is equal to q naught E vector. This is the relation between electric field and electrostatic force, because we have earlier studied the electric field is defined as electrostatic force experienced by charge q naught. So using this formula, I have written value of f as q naught into E vector. This will give dw equal to q naught E vector dot dx vector. In order to solve this dot product, let us consider this triangle. Angle between dx vector, this pp dash is dx vector, and E vector is 180 minus theta. So I can write q naught E dx cos 180 minus theta, because it is the definition of dot product a vector dot b vector is equal to magnitude of first a multiplied with magnitude of second b into cos of the angle between two vectors a b cos theta. In this case, angle is 180 minus theta. So I can write q naught E dx cos 180 minus theta is equal to minus cos theta. So the previous equation can be written as dw equal to minus q naught E dx cos theta. Now how to find cos theta? Value of cos theta can be found from this right angle triangle PMP dash. From triangle PMP dash, we can write cos theta equal to PM divided by PP dash, means base over hypotenuse. In this triangle, this is base, this is hypotenuse. Putting the values of PM and PP dash, PM I have supposed equal to dr, that is very small portion of length r, and length PP dash is dx. Now we shall put this value of cos theta in previous equation, and we get dw equal to minus q naught E dx dr upon dx. Now dx and dx can be cancelled, so we are left with dw equal to minus q naught E into dr. Now we have to put the value of electric field. Electric field at this point P, due to this source charge at distance r, can be written as E is equal to 1 over 4 pi epsilon naught q upon r square. After putting this value of electric field, we get small amount of work done equal to minus q naught upon 4 pi epsilon naught into 1 over r square dr. So this is the small amount of work done in moving the test charge through very small distance from P to P dash. The total work done in moving the test charge from point A to point B can be found by integration of this equation. So in the next step, I will integrate both sides. Thus, integrating the previous equation on both sides, we can write integration dw equal to minus q naught over 4 pi epsilon naught integration 1 upon r square dr. Now we have to put the limits of integration. We have started from point A and end point is B, so we can write A here, B here. Suppose the distance of point B from the source charge is RB, and distance of point A from source charge is RA. So accordingly, the limits on right hand side will be RA and RB. Left hand side gives answer for W equal to minus q naught upon 4 pi epsilon naught r raised to the power minus 1 over minus 1. Answer for simple integration. Limits are a, upper limit are b. After applying the limits, I can get W equal to Q naught upon 4 pi epsilon naught 1 upon RB minus 1 upon RE. So this result shows that total work done in moving the test charge from point A to point B within the electric field of this charge Q depends only on initial position and final position. It is independent of the path via which the charge has followed. So this is the condition for a conservative field. So we can say electric field is a conservative field. That's all. Thank you.